Hi, this is Mr. Yeager again, looking at simple harmonic motion, basically introducing the simple harmonic motion wave unit that we do together in this particular section. So if you haven't yet, one of the things I would recommend is to go to the It's Learning page and obviously looking at that neat pendulum video that I showed you. Again, that's one good example of simple harmonic motion. What is simple harmonic motion? It's basically what we're looking at today. And we're gonna break that down a little bit more into looking at simple harmonic motion of springs and pendulums. All right, and then next week we'll be looking more specifically at waves. So again, this is what we're going to look at today. What is simple harmonic motion? All right, there's lots of things that do simple harmonic motion. The classic one that pretty much everybody thinks of first would be ocean waves, just because they're so repetitive and they just keep on kind of slowly coming on in generally regular intervals. All right. You can always go to any of these links if you want just to see that. I mean, it's nothing more than just, a long video of ocean waves. Springs do simple harmonic motion. Pendulums do simple harmonic motion. Again, there's also a link with this one, if you're able to get to the original PowerPoint, to see, obviously, a neat pendulum effect. Okay? So, what is simple harmonic motion specifically? All right? It occurs when an object does a repetitive action over and over again. All right? What does that mean? Sorry, looks like my pen's going to be a little bit pain today. Okay? What does that mean? All right? Basically, what we're saying is that, the best example is kind of that wave motion, that up and down wave motion that you can put on a graph. All right? But also, just think of a pendulum. It goes back and forth, okay, over and over and over again. All right? We will primarily look at situations where friction is not involved, so it's something that will continue on forever. All right? It'll just keep going and going and going all the time. All right? As it goes back and forth, there won't be any energy loss. All right? But one of the key words already, the word oscillating and oscillation, that's one complete entire motion. Okay, somebody on a swing, that would be where they're already in the very back of the swing. They swing forward and then back. That would be one oscillation, not two. Okay, don't make it would basically be if I start here, going forward and coming back, that is one oscillation. Okay, one oscillation. Do not make the mistake of going 1, 2, 3, 4. That's not right. It is 1, 2, 3, 4. All right, we're trying to look at to and fro motion. There's a lot of different words that we use that are meant to illustrate the idea of a repeating occurrence. We could say pulses, we can say waves, we could say oscillations, we could just say times, okay? It's just something that's occurring over and over and over again. That's what simple harmonic motion means, all right? So if there's any sort of break in it, all right, if it's not a repetitive motion, if it's very uncoordinated, that's not simple harmonic motion. All right. Two big measurements that we're going to be using quite a bit throughout this unit, all right, is period and frequency. Now, period came up a little bit a while ago when we talked about circular motion, all right? But again, we did that because we said one complete circle, measure the time of one complete circle. So from where you started, coming all the way back again. We measured period as you moved around a circle. We're going to do the same thing with simple harmonic motion. Instead of measuring, a particular distance, it's how long does that occurrence take. So period is time, all right? The time it takes to complete one oscillation, time over oscillations, all right? So I could say, again, my poor pen just keeps going away. Get my pen back again. All right. I could say you have 10 oscillations, oscillations, there's my shorthand for oscillations, OSC, 10 oscillations in 5 seconds. What would the period be? Period would be 5 seconds over 10 oscillations, which then I would go down to 0.5 seconds. There is no unit for oscillations because it's a counting number, so we don't include it. And again, it could be a bunch of different things, pulses, any of those things. So period is simply in seconds, is measured in seconds, 0.5 seconds, all right, would be the period. So every 0.5 seconds, an oscillation occurs. That's what that's saying. Very much related to that, we have then what's called the frequency, okay, which you can see a symbol is F. That is the number of oscillations per second, all right? So see what I did there? It's the opposite. It's the inverse. All right. Frequency will equal oscillations over time. So if I redid the calculation above, the frequency would be 10 oscillations over 5 seconds, which would be 2. Well, what's the unit for frequency? It's going to be the hertz. Okay. The unit for frequency is called the hertz. All right. Sometimes we write it as a second to the negative 1 because basically it is a number over seconds. So a hertz, that is saying how many waves are passing over a second, how many waves are passing, how many oscillations occur. So obviously one very big thing, all right, they are inverses of each other. One thing that students sometimes get really bothered by is I give them the frequency and it says, what's the period? And they're going, why are you giving me the frequency? Why, don't I need the time over seconds? They are inverses of each other. So if you have one, you have the other. You just have to remember they are inverses. Okay? So that is very, very important. They are inverses of each other. All right. So already jumping into it. What are we going to use this period and frequency and stuff like that with? Well, the first type of simple harmonic motion I'm going to look at is springs. Okay? And so there are 3 things we actually are going to have to calculate out with springs. You're going to see pendulums is very short. There's not much to say about pendulums. Springs is a very popular device component in physics because it's something we could throw into basically any problem if we really want to. We're going to keep this pretty specific, basically saying how, what is the force of a spring, what's the potential energy. I'm not going to turn it into a projectile problem or anything else like that later on. So it's very specific. We have 3 formulas we're going to look at. All right, so here we go. So the first thing is there's a spring force. So this is another force that could technically be added onto a free body diagram. It's just like any other force. All right, the spring will provide a push or a pull. Now we have a specific formula for it. Spring force is equal to what's called a spring constant times its displacement. All right, its displacement. That is rewritten as, in simple form, force of the spring, FSP, will equal K times X, where K is the spring constant, newtons over meters, and X is the displacement from equilibrium. All right. What we have to think about, and you're going to see in a lab that you'll do later on during the week. Later on in the week, you're going to be looking at these situations where basically, I can hang a spring down from the ceiling, and it'll be fine. That would be its equilibrium point. All right, that would be, we would call this wherever the spring reaches to. This would be x equals 0 because what we're saying is the spring is not compressed or stretched. All right, that is what we mean by being at equilibrium. It's not compressed or stretched. It says that down at the bottom. What do we mean by displacement from equilibrium? Okay. Got to think of it like if you've used any springs or even like a slinky, you pull it apart. What does it want to do when you release it? Come back together. Okay, depending on how you're holding it. You might work out. There's obviously different springs used. You can obviously pull it, and then obviously if you let go, it's going to bounce right back. There's a force that's developed when you pull this spring away from equilibrium. If it's at equilibrium, it's not going to do anything. All right, there won't be any force. But if obviously if I start pushing this spring in, the spring is going to push downwards. Okay, if I compress the spring, the force of the spring wants to make that object move down. If I stretch the spring way past, which way does the spring want to go? It's going to create a force back up. So we're going to have to pay attention to that a little bit. It should be hopefully sort of common sense of, hey, if I pull the spring, it's going to pull back in the opposite direction that I just pulled. Okay? Now, what the heck is this spring constant? All right? Now, this can be, some people get a little worried because they're like, oh, cool. It's a constant. There's one number I can use, and we go from there. The thing is, this spring constant is based on the spring itself. So what we mean by that is every single spring in the world, you could basically say, has a different spring constant. And, essentially another way to look at it, it's the spring strength. It's how difficult is it to pull that spring apart. Again, there's going to be some springs that are very easy to pull apart, and there's some that you're sitting there pulling and pulling and pulling and pulling and pulling, and it barely goes anywhere. And that is the spring strength. It just might be tougher, okay? And that's not about being thick or anything. The example I always use is if you drive a car, you have shocks in a car, okay? It's the shocks. It's the shocks, yeah. Obviously, they're helping you try to make sure that when you go over a bump, you don't fly out of your seat. It's trying to absorb some of that, basically that motion. So those springs in your car to prevent you from bouncing around when you maybe hit a bump or hit a speed bump or anything like that, all right? They have a very high spring constant because they obviously are not going to stretch that much. It's going to take a lot of force to make it stretch, and so obviously that means it's not going to make you keep on bouncing for very long, okay? So that is the spring constant is something we often do try to solve for. We call it a constant because once you know it for that spring, you're done. It's going to be that constant no matter what situation you put that spring under. Okay? So it's constant for that particular spring. So you're going to see a lot of different questions where it's like the spring constant for this problem is 5. The spring constant for this one is 10. The spring constant for this one is 20. That means I'm using different springs. Okay? Last thing, displacement has to be in meters. You're going to get a lot of problems where this is in centimeters. So be very careful. All right, so stick and pen. Let's try a quick little problem here. Okay? Let's try a quick little problem. Okay? So if you have a spring, it has a spring constant of 100. So K is equal to 100 newtons over meters. Those are the units for spring constant because we're looking for force. And if I multiply this number by a distance, I'll have newtons left over. So it's the spring constant is 100 newton meters. What force would you have to apply to stretch it 0.1 meters? So you're trying to stretch it 0.1 meters from its equilibrium, basically. Okay. So what force would I have to apply? It's basically spring force equals 100 times 0.1. So it would be 10 newtons. I would have to pull that spring 10 newtons. All right? I would apply 10 newtons of force. What force does the spring apply on you? This is kind of a third law problem. If I pull 10 newtons, what's the spring going to pull back? 10 newtons. Okay? 10 newtons is what we're looking at there. Okay? Obviously, equal opposite forces being developed. I'll lose it again. There we go. Too bad. All right. This is going to be a more common problem. You're going to probably get the first one too, just so we know you can use the formula right. Whoop. Okay. And so this is going to be pretty common. All right, because this kind of extends it a little bit more back to like an old unit on forces. So you hang a 2 kilogram mass onto a spring that has a spring constant of 500 newton meters. How far will the spring stretch if the mass is hanging at rest? Boom. The object is at rest. The first thing I would do here is draw a free body diagram. We haven't had to do one of these in a while. I would draw a free body diagram. So the idea is, I'll draw it out. Basically, you have something on a spring, hanging on a spring like this. Okay? When the object was not on the spring, basically you could say we got something like this. So the idea is, this is the one on the right here has no mass. When I've added the mass, how much have I displaced the spring is what I'm looking for here. Okay, away from equilibrium. So with the free body diagram, this would be weight down, pulling the spring down, but the spring is pulling the object back up. But the thing is, the object is not moving. So what can you tell me about these two forces? They must be equal. The net force on this is 0, which would equal spring force minus the weight. So again, they must equal each other. So how would I solve this? Well, I know formulas for both of these. Spring force is K times X, weight is M times G. Plug everything on in. So it's going to be 500 times X, I'm looking for the displacement, X, equals 2 times 10, 500 divided by 20, what's that, 25, I believe? Yeah, it's 25. X would be 25 meters. That would be a heck of a spring. All right, a little silly there. Oh wait, no, I'm doing this all wrong. Let me try that one more time. I'm going from the wrong side. Apologies. I'm trying to go too quickly here. All right, I'm being silly. This should be x equals 20 divided by 500. I knew that didn't make sense. 20 divided by 500. 20 divided by 20 divided by 500 would be 0.04 meters. That makes a lot more sense. I'd be surprised to see a spring stretch 25 meters. All right, so that's only 4 centimeters. That makes a lot more sense. Okay, so there you go. This is very common. You'll see these problems. I can almost guarantee you. Basically, hanging an object on a spring at rest. Those forces are equal. Spring force equals weight. Solve for, it's going to be any of these things, K, X, or M. I could really ask for any of those. I could even say you go to another planet and solve for G. Okay, so you're going to get plenty of examples with those. Okay. All right. What about, so that's spring force. Spring force K times X. K times X. Spring constant times the displacement. Well, for spring potential energy, there is a energy from the spring itself, because again, it has the potential to make an object start moving. And usually, think about if you compress, any toy gun is basically spring loaded. All right, and when you compress it, you're storing up energy that when you press the trigger, boom, that object shoots out with an appropriate amount of kinetic energy to make it move. So, elastic potential energy or spring potential energy, they're basically known either way. Its formula is 1/2 kx squared. So same units, k and x. K and x. So if you know how to solve for force, you can solve for the energy as well. So the same exact variables, but instead we have the 1/2, and we're going to square x in order to solve for joules, okay? To solve for the energy in the system. All right? So if we do this particular problem once more time, oh my gosh, how many times do I have to keep on grabbing my pen? All right. What is the elastic potential energy for a spring with a spring constant of 100 Newton meters, stretch 0.5 meters? Just plug it on in. Equals 1/2 times 100 times 0.5 squared. 0.5 squared. So if we get that one, the elastic potential energy should equal 12.5 joules. Okay? 12.5 joules. And again, obviously, the more you displace the object, the more energy is going to be within the spring and the object itself. All right? So, again, since they're the same numbers, you could get a problem that says, what's the force that's being produced? What's the energy that it has? Because we just have to use the correct formula for it. Okay? All right. Other types of questions, all right? Other types of questions you will see with springs, all right? And you actually, again, are going to do a lab with this, but I mean, we could basically already go over some of the answers, all right? Explain the change in elastic potential energy while a spring bounces up and down, okay? As it zooms up and down, up and down. It doesn't even have to be up and down. It can be displaced left and right as well, okay? So, explain the change in elastic potential energy that occurs. So again, what we're looking at here, I'll do a horizontal one, is basically, let's say you have a spring. This is at x equals 0. What would happen when you stretch the spring, when the object is all the way stretched out, let's just say at a distance, A, positive A, amplitude, okay? We'll talk about amplitude later. And then how about when it's pushed in? How about when I compress the spring, negative A? Where would I have the most potential energy? The answer is at the ends of the oscillation on either side, on the left and right side. All right, it's going to be at the ends. All right, or again, if I'm looking from a top-down view, it would be when it's obviously stretched or compressed. Okay, so it'll have the most at the ends of the oscillation when compressed, completely compressed, or stretched. All right. When will the elastic where is the elastic potential energy the smallest? All right. And again, we like to do this where the object's not just sitting there, it's bouncing up and down, bouncing up and down. There would be no elastic potential energy where? When x equals 0, so basically at the equilibrium points. At the equilibrium points. All right, that is where you're going to have 0 because, again, that's where x equals 0. All right, so you'd have no energy. All right. All right, last question. All right, and this one's a tough one. If I double my displacement, how does that affect my EPE? All right, we haven't had one of these questions, I feel like, in a little bit. You had some in electricity. Okay, so if I double my displacement, well, what do we have to think about this? EPE equals 1/2 kx squared. So as I said, of how we try to do these problems, we eliminate everything that won't change. So EPE is going to be related to x squared. So think about it. If I double x prior to squaring it, which is what it is basically saying, what's going to happen? This is going to come out to 4x squared. My original relationship is just EPE is related to x squared. What have I added to this formula now that I've doubled it? It will be 4 times the energy. It'll be 4 times the energy. That is the change we're going to see because it's square. If I triple the distance, it'll be 9 times. If I quadruple, it'll be 16 times as much energy. So be aware of something like that. A question related to that. We'd like to do those. You can always go ahead and plug in numbers. You can pick out a k. You can pick out you can plug in 1 and 2 for x, and you'll again see that when you double the distance, it should quadruple your amount of energy. What can we change about a spring? All right, so now we're getting to period. And again, period is the time it takes to complete one whole oscillation. All right, what can we change that could possibly affect the period of a spring? So what we're looking at now is we'll actually pull the object away from equilibrium, let go, and it's going to start oscillating back and forth. You have this little spring going up and down, or left and right, left and right. So what's something you could try to alter about that particular spring? Okay, one is we could, and again, I want to make sure this is clear. It says mass of spring. I should have that as mass on the spring. What is the mass at the end of the spring? Not mass of spring. It's a little misleading. I don't want you to get confused. There's all your answers. Okay, the mass of the spring. Okay, sorry. The mass on the spring is what I should be saying. Okay. So the mass on the spring, what mass do you have at the end of it? Could that change the period? We'll figure out in just a second. All right. So that could be an idea. Okay. So again, that's what we're trying to say here is again, that's the object at the end, not the actual mass of the spring. We're going to basically say the spring is massless. Okay. So that's one example. All right. We could possibly get a stronger spring. We could go to a different spring and get a larger spring constant. So that would be related to K. All right. The other thing we could do is we could obviously test this by pulling the spring 1 centimeter and measuring how fast it goes back and forth. 2 centimeters, measuring the time it takes to go back and forth. 3 centimeters. So that would be the displacement of the spring. The thing is, out of these 3 things that we can alter, only 2 of them actually affect the period. Only 2 of these. All right. So try to think. What could possibly affect how much? Which one do you think will not affect how quickly this thing will go back and forth? All right. And again, don't be misled by when I say quickly. I'm talking about time. Which one will affect the time? Having it go either faster or slower, completing one entire oscillation. So it turns out that mass and spring strength will change the period. Mass and spring strength will change the period. Okay? And we have a formula. Okay? I'm sure you're getting tired of this. I am very sorry that this keeps on happening. All right? And again, mass has to be in kilograms. That's the first thing. Make sure you're always in kilograms. But this formula is 2 pi times the square root of m over k. So we get some kind of stranger formulas, but these are going to be mainly a lot of just plug in the numbers and solve, and hopefully you put everything in correctly. All right. So the period of a spring is 2 pi times the square root of m over k. And it basically shows you, hey, if I increase my mass, that means I'm going to increase this quantity right here. That should increase the period, meaning, our answer down here, a larger mass will have a larger period. It will take longer. Why? There's more to push. Okay? It basically goes back to Newton's second law. The larger the object, the less the acceleration it will have. So it won't accelerate back and forth as quickly. All right? Is basically what you're looking at there. K is involved, the spring strength. That makes sense. Obviously, a stronger string is going to be able to pull that object back more quickly or push it out more quickly. So that is what, those are your two main factors. Now, really quickly, why does displacement not affect it? Why does displacement not affect it? What you need to think here is, and this is why I'm sure some people thought, hey, displacement would make it go faster. You're right. All right, you're right. It would make it go faster. If I stretch it 2 centimeters and then I stretch it 10 centimeters, the spring will go faster eventually with the 10 centimeters, but what does it have to do? All right? So even though displacement will increase the velocity that the object goes because you have more energy, you are also increasing the distance it has to travel. Object travels. And so what happens here is it turns out the time, the period, will remain the same. The period will remain the same. All right? So it will increase how fast it goes, but then it has to travel farther. I mean, what the 2 centimeter object only needs to basically travel between 4 centimeters. This 10 centimeter setup will have to travel back and forth 20 centimeters. That's going to take longer. So the only two things that affect it are mass and spring strength is all we're looking at. Okay. So what is the period of a spring? If it oscillates 10 times in 20 seconds. Sorry. 10 times in 20 seconds. All right. Well, that one, again, it's not making you try to use the formula yet. It's just trying to go, do you know what period stands for? So period is time over oscillations. If it oscillates 10 times in 20 seconds, so 20 seconds divided by 10 equals 2 seconds. The period of this spring is 2 seconds. If the spring has a spring constant of 5 newtons meters, what is the mass on the spring? So now I would do I'll write the formula, T equals 2 pi times the square root of m over k. So this would be 2 equals 2 pi times the square root of m over 5. The way I would solve this, and be very careful, it seems simple, but a lot of people make mistakes. I'm going to first divide out the 2 pi. Make sure you divide 2 pi. If you plug it in your calculator as divide 2 pi, most of the times it will divide by 2 and then multiply by pi. So be very careful there. So if I do this correctly, I'll go ahead and do this step by step. 2 divided by 2 divided by pi. I get 0.31 equals the square root of m over 5. Now I need to get the m, which is underneath the square root. What do? I square both sides. And that's the other thing. Always divide out that 2 pi first and then square. If you don't, most people forget to square the 2 pi. And that's just a lot of work anyway. So square. Now this is 0.101 equals m over 5. And then I just multiply by 5. So the mass of this object is 0.507 kilograms. 507 kilograms. All right. So that's period for springs. I think we're almost done. Yep, on the pendulums, So that's springs, force, energy, and period. For pendulums, we really only are going to be calculating the period of the pendulum. We'll talk a little bit about energy, but there's no calculations. It's all conceptual. It's what we did back in the energy unit. That's why we don't really worry about it too much. We already know if a pendulum's swinging back and forth, it's switching between gravitational potential energy and kinetic energy. Gravitational energy is the highest on the sides, lowest in the middle as it's passing through. Kinetic energy is lowest on the sides because it stops for a moment. fastest and highest through the middle. So, you'll again do another lab with this, confirming these details. Factors that could be changed about the period of a pendulum. Okay, we could change the mass at the end of the string. We could change the length of the string. And once again, we can change the amplitude. This would again be basically the idea of displacement, how far away from equilibrium. This is height, though, for a pendulum. All right. On the lab, I'll say an angle. I'll say pull it 30 degrees up, and you'll see that during the lab part of it. All right. So only one of these actually affects the period, though. All right. Springs had two factors. There's only going to be one, and that factor is length. All right. So again, you can see a very similar formula there, except with two new factors. Technically, we'd also say gravity can affect it, but that's something you can't change in the laboratory. All right. So this is again going to be the period of a pendulum. Put a little p right there. Is 2 pi times the square root of L over G. The only factor that's affecting it is L, is the length. All right. And again, like I said, gravity will too, but again, you don't have the ability to change that. So why will length affect the period? The idea here is if you have a shorter period and you have a longer period, okay? What happens is if I pull them both up the same angle, all right? Basically think about the distance it has to travel. All right? There's a larger arc distance, okay? You basically increase the arc distance that it has to go for a longer pendulum than a shorter pendulum. So the shorter the pendulum, okay, or sorry, yeah, I'll say the shorter the pendulum, if I decrease L underneath the square root, I'll decrease the period. The square root will become a smaller number. Now, why don't mass and amplitude affect the period? Well, I'll go and tell you again. Amplitude, basically the same reason why displacement didn't affect the spring. If I pull that object up higher, what's going to accelerate it? Only gravity. Gravity is always going to accelerate it the same. It will obviously accelerate longer and therefore go faster, but it will have to travel farther. Okay? So as long as you keep the length of the string the same, you can pull it up just a little bit or pull it up a whole 90 degrees. Obviously, this one will go a lot faster, will move a lot faster, but it will obviously have to travel a whole lot farther back and forth. This one right here, back and forth, done. May not look like it's moving fast, but it's completing in the same amount of time as the longer one, okay, or the larger amplitude. Let's be specific. All right. What about mass? Why will mass not affect it? Okay. I have a lot of people that think, hey, if I have a small mass and then I have a huge mass, the huge mass will go faster. No, it won't. Once again, both of these objects are going to be accelerated by what? Gravity. And everything gets accelerated exactly the same. We will ignore friction. We'll ignore air resistance. We don't bother with anything like that. Pendulums really aren't affected by those too much. All right. So that is what it'll be. They both are affected by gravity equally. So the only thing that's not affected by gravity is the length of the string, obviously. And again, that's related to the arc distance. All right. So if we do a quick problem, I think this is the end. We'll go through it together one more time. Here we go, here we go. Yep, we're on the last slide. If you have a pendulum on Earth that has a length of 0.5 meters, what would be the period of the pendulum? So T would equal 2 pi times the square root of 0.5, and I just like to use 10. Again, you can use 9.8. All right, in AP Physics, we actually, they're encouraged to use 10. The AP committee says use 10. All right, obviously, it depends on the teacher. Some teachers are so sticklers say it'd be 9.8. 2 pi times square root of 0.5 over 10. Let me solve for that real quick. I'm getting basically 1.4 seconds. 1.4 seconds. I'm going to do that one more time just to make sure. Yep, 1.4 seconds. All right. You'll get these theoretical problems if you're on Jupiter, G, 24.9. What would the period be? Okay. So basically, T would equal 2 pi times the square root of 0.5 over 24.9. We should already sort of know what should happen. I'm increasing the g, the gravity. So then this number underneath the square root is going to get smaller, so I should get a smaller period, obviously. More gravity, it's going to go faster. So 0.5 divided by 24.9, square root times 2 times pi. I'm getting this to come out to be 0.89 seconds. All right, it'll only take 0.89 seconds for that pendulum to go there and come back. All right, so those are your main ideas. Again, we're looking at springs has a bit more to it. You're going to get some practice with the formulas. Watch out for centimeters. Convert centimeters to meters and just plug them on in. All right. Obviously, when we get to period, there's a little bit more conceptually bound stuff saying what will affect, what it won't affect, and then obviously some relationship questions. And you'll get some good practice in a couple quick labs where you're looking at energy for springs on one, and then basically doing the classic pendulum experiment that is done in essentially every physics classroom but online in this case. All right, so thank you very much, and we'll go from there.